All right, I think we got everything working. Sorry for the delay, but it seems like it's okay at the moment. So we'll proceed. So for the last kind of thing that we're going to be talking about here in Chem 103 this semester, we're going to review a little bit of what we already talked about with carbohydrates, but then also more specifically talk about food and how carbohydrates work, and particularly sweeteners, sugars and sweeteners work in our foods. I've got some pictures here, and we'll look at some other structures as well, as we did with when we talked about the macronutrients. These are pretty big things, so I'm not going to draw the whole thing. It would be extremely boring, and it's definitely not something you have to be able to do. So let's take a look at some of these structures. So this first part is a little bit of review here. Again, if you have any questions, as usual, you can leave them in the chat or on Discord, and we'll get started. So the carbohydrates are named as such. We talked about this before because they have approximately a 1-to-1 ratio between carbon and water in their chemical formulas. That doesn't mean they're actually made of water or something. It just means that's how the formula works out. Ratios, so there's usually like 2 hydrogens for every carbon and oxygen. So you get formulas like this, C6H12O6. And that's not always the case, especially as they get bigger. They start to lose water when they connect, but that's the basic idea. So, all right. So we looked at some sugar structures before. There's a couple different ways that we talk about structures of monosaccharides, simple sugars. One is this thing called a Fischer projection, which is kind of a hybrid of a line structure and Lewis structure. These middle carbons are not shown, but everywhere there's an intersection is a carbon atom. They're very straight 90-degree angles rather than the zigzag that we know is actually the case in 3 dimensions. And that's just for like a diagram for ease of figuring this out. All that stuff about 3-dimensional geometry of carbon atoms wasn't really known at the time that this stuff was first being discovered. So this was sort of their best guess as to how to put this together. And it actually changes the sugar that you're looking at, whether the OH and the H are on the left or the right. So this is glucose, but if we switch those OHs and Hs, we actually get a different sugar, a different molecule. Sugars are known as either D or L, which is an indication of their like handedness, like left and right handedness, and specifically what they do when light shines through them in a particular instrument. We don't need to really worry about that, but most naturally occurring sugars are D sugars, and we can also encounter the L ones, but like when we talk about just normal glucose, we're talking about D glucose. All right. So there's other forms that these also find themselves in, which we looked at before. Also, so the Fischer projection here shows a straight chain type of a sugar. We know that in reality it's zigzag, but it's straight, meaning not connected in a ring. And so there's an equilibrium that develops between that and this ring-like structure. So this oxygen down here can come around and grab the carbon there, and the whole thing kind of twists over on itself. And then rather than a carbon double bond to oxygen, we have an OH up here. So that leads to this type of a structure. This is called a Haworth projection, where we see that ring, but everything's still very flat. That still is not a depiction of the realistic bond angles. To do that, we have to draw a structure more like this. And this, you can see those like tetrahedral carbons here, those 3-dimensional carbon structures. That's really more what the structure would look like in terms of the angles and the positions in 3 dimensions. But we do this just because it's easier to look at. When you look at this one, it can be hard to tell which ones are up, which ones are down, and that's important to that identity of the sugar. So in this case, we can see very clearly OH up, H down, H up, OH down, and there's this kind of alternating thing with glucose. If those OHs and Hs were to flip, you'd have different sugars. So you might have galactose or allose, or there's various different ones. You can look that up if you're interested. So that's our basic monosaccharide, simple sugar. Now what can happen is You can take two of these monosaccharides. In this case, I drew galactose and glucose. First of all, let's just take a minute to see what the difference is between galactose and glucose since they're right next to each other. They're very, very similar sugars, but galactose has this OH in the back here going up, whereas glucose has it going kind of down and to the side. So even just that very subtle difference makes for a totally different sugar. It's going to be processed by the body differently. It might interact in certain ways with certain proteins. I don't know all of the specific physiology, but that is an important difference, even though it seems extremely small. So if we do a condensation reaction, just like we talked about with the biodiesel stuff, the opposite of that, we can lose water, H2O, so HHO. Those go away and become water. And then the oxygen that was there connects to the carbon connects to the carbon on the glucose, and that makes a disaccharide. And the particular connection there is called a glycoside bond, that connection of the two. And if you want more detail on this, go back to where we talked about the macronutrients. We went through this as well. So here's our glycoside bond and our disaccharide, two monosaccharides, two sugars hooked together. And this one is lactose. That's milk sugar. So when we talk about people being lactose intolerant, it's this particular molecule that can't be broken down properly by the body, even though other disaccharides like sucrose, table sugar, can be easily broken down. And so that just kind of illustrates how these slight different positions in the OHs around the ring actually lead to pretty different structures when we talk about how this interacts with enzymes inside your body. So here's a picture of sucrose that I drew. Sucrose is a little bit weirder looking because it's a disaccharide of glucose, which is a 6-membered ring. 1, 2, 3, 4, 5, 6. And fructose, which is a 5-membered ring. 1, 2, 3, 4, 5. So you've got the 5-membered ring here for fructose, and you've got the 6-membered ring of glucose here, and they're connected through that same glycoside bond. So when we talk about just sugar, the white stuff that's in your pantry, that is this right here, this sucrose. And as we mentioned before, get there in a second, that in the body, this can be broken apart and produce glucose and fructose that can then be broken down further. This also sometimes happens in foods. So there is a commercial product you can get, you don't usually get it in the store, called invert sugar, where you take sugar and enzymatically break it down or acidically break it down. If you cook this up with some acid, just weak acid, you can actually break this glycoside bond and you can make glucose and fructose kind of together. And that is a different substance that's often used as an industrial sweetener. So if you see something that says invert sugar in ingredients, that's what it is. It's the same as sucrose. It's just like pre-broken down, basically. Another interesting thing that happened a number of years ago, if you've ever had the Mexican Coca-Cola that comes in the glass bottle that you can get imported into the store, if you look at the ingredients on that soda, it says sugar. And it does not say high fructose corn syrup, which is another sweetener we're going to look at in a minute, which is more commonly used in like the regular plastic bottled Coca-Cola that you see at the store here in the US or in cans. So people thought, oh, well, it's sweetened with sugar, so that must be sucrose, so that's different. But actually some lab analysis done on that particular sample showed that there wasn't any sucrose in there. There was glucose and there was fructose, but there was no sucrose. And so the either it was a type of a high fructose corn syrup, and there's just sort of a regulatory difference where they are calling that sugar in Mexico, or you actually put sucrose in there, but because of the high acidity of the Coca-Cola, the phosphoric acid, perhaps over time, it actually breaks this thing down and sort of makes its own invert sugar out of the sucrose. So that brings us to our next idea, which is high fructose corn syrup. So let's talk about high fructose corn syrup for a minute. This is a common sweetener in the US. You've probably heard of it. What it is you get the syrup from corn, which is regular corn syrup, like Caro syrup or something. If you ever tasted that, it's not as sweet as sugar. So what you can do is you can do some chemistry to that corn syrup, and you end up kind of doing what we just talked about. You end up breaking down not only the sucrose, but some other saccharides in there as well, and forming some more fructose. Now, fructose is a 50-50 component of sugar, of regular table sugar, so 50% fructose, 50% glucose. But when it's broken apart, fructose is actually sweeter than sucrose, and glucose is less sweet than sucrose. So when you break that apart, so different sugars have different sweetness levels, and so when you liberate that fructose, it makes it taste sweeter. And so most high fructose corn syrup is about 55% fructose, so just a little tiny bit more than regular sucrose, but it's free liberated fructose, which means it's going to be a little bit sweeter. And the interesting thing about there's a couple interesting things about high fructose corn syrup. One is that it was developed specifically to be a exact sugar substitute. So they did lots of experiments with different formulations and found that this high fructose corn syrup was indistinguishable to tasters from regular sugar. So if you believe that something tastes different to you if it's sweetened with high fructose corn syrup or sugar, there's something else going on there. You're fooling your brain, or there's other flavors in there that are changing it, or the sweetness levels aren't equalized, whatever. But if you actually do controlled experiments, people cannot tell the difference between the taste of high fructose corn syrup and sugar. Another interesting thing about high fructose corn syrup is it really has two advantages in industry, and the reason that it's in all of this food. One is that it's a liquid sweetener, whereas sugar is a solid. And it's a lot easier for industrial equipment to handle liquids than solids. You can, pass it through all kinds of easy dispenser, squirter, machine thingies. Whereas with solids, you need some more complicated equipment. You need to measure by mass instead of volume. And so it's a lot harder to deal with. So they like the high fructose corn syrup for that reason. And then for a bad reason, that makes it much easier to put in lots of things. And since we like sweet tastes, it makes it easy for us to fool us into liking something. So for example, fast food restaurant buns and Wonder Bread, like white breads, those kinds of things. Even some of the like sweeter wheat breads, like the Sara Lee and butternut and stuff like that. They'll have high fructose corn syrup in the bread, because it makes it taste better. It makes it sweeter. It makes us like it more. Do you really need to be adding more sugar to your bread? No. But that's going to make people buy it more and like it more. And it's one of the problems now with our food system is that we are adding this extra sugar to basically everything. Now, whether it's sugar or high fructose corn syrup doesn't really matter from a health standpoint. The bad part is that there's more sugar, of either sugar in foods that don't really need it. Other sweeteners also have a lot of fructose, like agave syrup, for example, has 80% fructose, so really, really high fructose, and much, much higher than high fructose corn syrup. The other reason we use high fructose corn syrup is tax policy. We highly subsidize the growing of corn in the United States. We give farmers lots and lots of money to keep corn prices way, way down. And so anything we can make from corn ends up being way cheaper because of those government subsidies. And then conversely to that, a lot of our regular table sugar, especially that which comes from sugarcane, is not grown in this country. It's grown in South America and Central America and the Caribbean, places like that. So that sugar is subject to taxes or to tariffs when it's imported into this country. So corn is cheaper, sugar is more expensive. So if you can sweeten your foods with corn, you can save a lot of money. Not like naturally saving money. The government is helping pay for that basically. So the U.S. government, taxpayers, however you want to say that, is really subsidizing high fructose corn syrup, making it a lot cheaper than sugar. We do produce beet sugar, so sugar that comes from sugar beets is produced in the U.S., but not sugar cane mostly. All right. There's questions on that stuff. I don't see anything. Okay. So the last thing we're going to look at then is non-nutritive sweeteners. You've probably heard of some of these. So these are sweeteners that give you a sweet taste, but do not provide nutrition, do not provide calories. And there's a few different ways that they do this. Primarily, these types of molecules are hundreds and hundreds of times sweeter than sugar. So something like Splenda sucralose, I believe, is like 800 times sweeter than sugar. It might even be more than that. So that means you need 800 times less of the actual chemical. So when you get a packet of Splenda, it's not the pure chemical the way it would be with sugar. It's actually mostly maltodextrin, which is like a soluble fiber. It's just, like nothing. And it's coated with a very, very thin layer of sucralose because you really only need tiny, tiny micro fractions of a gram to have the same sweetness level as you would with sugar. And that's the same thing with aspartame. It's not quite as sweet. There's an older sweetener called saccharin, which we don't use so much anymore, but it's the red packet. Some people really love it. If you grew up with it, you probably still like it. If you grew up like drinking Tab or I don't know, Fresca, weird stuff like that. I shouldn't say it's weird. It's just, that was the first like diet soda type stuff. Most people now don't care for the flavor. Saccharin has like a very bitter, kind of almost metallic flavor to it. And then there are some newer sweeteners like stevia and neotame. And let's take a look at some of these structures so you can see chemically what's going on here. All right, so it looks like the test is a little bit blurry, but hopefully you can see it. I'll move around here. All right, so we'll start with aspartame because that, I believe, is just being surpassed now by sucralose, but for a long time, that was kind of the king of these non-nutritive sweeteners. Aspartame is this structure right up here. It is 200 times sweeter than sucrose, and it is also known as equal or NutraSweet. It's the main sweetener in Diet Coke, Diet Pepsi, Coke Zero, all of the diet sodas pretty much. Anything that's sugar-free, Crystal Light and those types of like powdered drink mixes that don't have any sugar. Excuse me. That's primarily aspartame. Again, it's kind of being taken over by sucralose now, but for a long time it was this. So aspartame, if you notice molecularly here, it really doesn't have anything in common with the carbohydrate structures we just looked at. It doesn't have the ring with the OHs coming all around the sides. It's not multiple saccharides mixed linked together through glycoside bonds. Aspartame is actually amino acids. Aspartame is it's a dipeptide. It's two amino acids linked together. This over here is, that's not a pen. This over here is aspartic acid, which is an amino acid. And then this part over here is phenylalanine, which is an amino acid. And there's also this little kind of extra methyl part. So it's methyl phenylalanine aspartic acid. So you've got these two amino acids linked together, and it just happens that this combination of amino acids tastes very sweet to us. And that's why this thing works. Now, it being an amino acids also helped with things like safety because we know how amino acids and proteins and peptides are processed in the body. And there's now decades and decades of research behind aspartame that at normal consumption levels, we've never really found evidence of negative effects. Now, there's a lot of conspiracy theories around aspartame. A lot of, like diet sodas are worse for you and the sweetener does all this weird stuff to your body, but there's really not evidence of that. At very, very high consumption levels, this can be dangerous, but you're talking like, a lot. I don't know the numbers offhand. It's you have to drink a lot of Diet Coke to get to those kinds of levels. They do exist, but there are warnings not to exceed that consumption. The other thing that freaks people out about aspartame sometimes is that products with aspartame, products sweetened by aspartame, have a warning on them that says, attention, phenylketonuria contains phenylalanine. There is a relatively uncommon condition in humans called phenylketonuria where your body cannot process this amino acid phenylalanine, and it's a pretty serious condition. It means you can't have meat. It's hard to avoid this amino acid, and so if you have that condition, you have to be really, really careful about what you eat, and your diet is quite limited. But those people definitely do face a danger from aspartame because of their inability to process phenylalanine. Some other common sweeteners that we see. So the big one now that's starting to overtake phenylalanine is sucralose, which is also known as Splenda. It is much sweeter than sucrose. It is a sugar structure. In fact, it is sucrose structure with a couple changes, chlorine atoms being put in place of some OH atoms. Otherwise, the structure is virtually the same as sucrose. So this makes it much, much, much sweeter. So you use much less of it, and that's why it's kind of taken over. There are some other ones as well. Neotame is extremely sweet, thousands and thousands and thousands of times sweeter. So sometimes you'll see that in very, very tiny, tiny amounts. I haven't heard of this one. This must be a newer one. Advantame, 20,000 times sweeter than sucrose. This is another amino acid-based sweetener. And then you've got the old one, saccharin, over here. This one also doesn't look like a sugar at all. It has its own structure. This is probably the oldest one in the U.S. It says marketed in the U.S. as a sweetener for around 100 years. So all the early non-sugar stuff like Sweet and Low and those early sodas were sweetened with saccharin. There was also some panic about saccharin. For a while, any products with saccharin had to have a warning label that this product contains saccharin, which is known to cause cancer in laboratory animals. And that certainly scared people away, with good reason, I think, from using saccharin. But in the years since that experiment, those experiments have been repeated, and that was not found. And it turns out that the particular mice they were using, the strain of mice that they were using at the time, were just mice that were really likely to get these particular types of cancer tumors. And no matter what you feed them, they get these tumors. So it wasn't really a properly controlled experiment, and it's actually not the saccharin that was causing the cancer. So those products no longer carry that warning because it was debunked. So it's doesn't cause cancer. And then you have newer ones like this, stevioside, which is a molecule that is grown in the stevia plant. And so things like Truvia, stevia, those types of sweeteners are these types. One thing that I think is interesting about these is they are marketed very heavily as being somehow better because they're all natural, but they're really not. They're the same. It's a molecule that tastes much sweeter than sugar, so you use a smaller amount of it. The only difference is this one's made by a plant. And just in general, that shouldn't really give you comfort. The plants make lots of really bad stuff. All of the most dangerous, most toxic substances we've ever known were all biologically created, like, botulinum toxin, so forth, which is created by a bacteria, not a plant. But there's lots of nasty stuff that plants create, lots of things that you can't consume that are really bad for you. So the fact that something created by a plant should be favored over these other ones doesn't really make any sense scientifically. So just watch that, because marketers are always out there trying to get you to pay more for something. And if they can sell you that, hey, this stevia sweetened beverage is more natural and better than this cheaper sucralose flavored one, then they're going to try to really push that. And you now have the skills to look up that research, to find the real stuff that's going on, to look at the studies and figure out what the real truth is. Don't just believe what you hear from advertisers or non-scientists or people on social media or whatever. So all right, so that's artificial or non-nutritive sweeteners. Another reason that term has changed a little bit because of these naturally occurring non-nutritive sweeteners. We don't always say artificial sweeteners anymore because some of them are naturally occurring, but they still are in the same category. They're still doing the same thing chemically. And so the fact that they come from a plant source doesn't really change that. And so now the category is more called non-nutritive sweeteners or non-caloric sweeteners or something like that. All right, so that's a little bit about sugars and sweeteners. If that may help you read through some of those papers from Blackboard last week or last couple weeks, and if your project is in this realm, that may help you there as well. Although you're of course not obligated to choose any particular topics. So I'm looking forward to reading your final reports next week, and have a great weekend. Bye.